Hello and welcome to SAS Junior Math. Today we are going to be looking at how we can solve questions on exponential equations with different bases. In our last video, we looked at how we can solve exponential equations and in such a way that we're going to reduce the base to its lowest common base. It means that on the left hand side, the base on the left hand side and the base on our right hand side were the same. But in this case, the questions we are going to be looking at now to solve are questions with different bases. How do we solve questions with different bases? In such a way that no matter how you break them down to their lowest common basis rather, it will not be equal. Let's look at the first example. We have 3 raised to power x equals to 6. 3 raised to power x equals 6. If you look at 3 and 6, you will realize that the bases are not equal. And no matter how much you try to break the right hand side to look like the left hand side, it will still not be equal. So what are we going to do? Now, we are going to be introducing a technique and that is logarithm. So we are going to take log on both sides of the equation. Why are we taking log on both sides? We are taking log on both sides because logarithm has its natural base, which is base 10. So if we take this logarithm on both sides on base 10, it means we are going to be operating on the level of equal bases. Let's not forget that initially it was 3 and 6, but now since we have introduced natural log, so we are going to be operating on log 10, log 10. So at the end of the day, the base on each side of the equation will be the same. So let's take log on both sides. So take log on both sides. Take log on both sides. So from here we have log 3 raised to power x equals log 6. I can as well write log 10, and I can as well leave it the way I left it the other time. Now, after introducing log on both sides, we are going to introduce one of the properties of logarithm, which is called power law logarithm, as in the power law, one of the laws of logarithm. And the power law of logarithm here states that if you have log a raised to power x in base n, then it's the same as saying x log a base n. So this law is known as the power law of logarithm. So let's look at it again. It states that if you have log a raised to power x base n, you can as well say x, this power has to come to the front, log a base n. That is what this power law is talking about. And the reason why we need to introduce this logarithm is, one, to make sure the base are equal, and secondly, to isolate x or to make x stand alone. So what are we going to do from here? If you look at it now, you see that they look alike, they go together. So from here, I'll write this again: log 3 raised to power x base 10 equals log 6 raised to power log 6 base 10. Then from there, I can say this is same as saying x log 3 base 10 equals log 6 base 10. Then the next thing I'm going to do is to divide both sides by log 3 base 10. So we have x log 3 base 10 equals log over log 3 base 10. This is going to be log 3 base 10. So when this cancels, I will have x equals log 6 base 10 over log 3 base 10. So from here, I will say x equals to, so I'll do a quick check on log 6. My log 6 is 0.7782 divided by, let me check log 3. Log 3 is 0.4771. Then I'll do a quick division of them. 0.7782 divided by 0.4771. And I'm having 1.6311. And that is my answer. Then I can do a quick check. So I can check if I'm right or wrong. So how do we check? To check, substitute the value of x into this equation. So we have 3 raised to power, what's our new value of x? 1.6311. So we want to check if it is equal to 6. So what is 3 raised to power 1.6311? So we have 6.00, and you can see that it's approximately 6, or it is 6, whichever way, because I approximated this, and we have decimals and so on. So one of the differences here between exponential equation with the same base and exponential equation with different base. And mind you, please take note of something. Exponential equation with common base does not mean that from the starting it has to be the same base. Like for example, 2 raised to power x equals to 2 raised to power 3. It doesn't have to come in this form. It may come in a different form. Instead of 2 raised to power 3, you may see 8. But we all know that we can as well raise 2 to a certain power in such a way that at the end of the day we are going to get 8 as our answer. So in that case, we have succeeded in taking it to its common base. What do I mean? What I mean here is that you may see 2 bases that are different, but you can as well take them to their lowest common base. But in this case, we cannot do anything like that. It's not possible for us to break this one to be 3 raised to power something that will make this other side to be equal. So the difference here is that for lowest common base, the value of x you get is always a whole number. But for exponential equation with different bases, the value of x you will get in most cases will always be in decimal form that you just have to keep approximating. So when you solve for the value of x, if the value of x is approximately to what you have on your right hand side, then it is okay. So now let's move on to the next question. Now, number 2 question says 4 raised to power x equals 7 raised to power 2x minus 6. So we are going to follow the same pattern. So we take log on both sides. Take log on both sides. So we have log 4 raised to power x equals log 7 raised to power 2x minus 6. Then, as soon as you write this, then we introduce the power law of logarithm by saying that the power here moves to the front of logarithm. So it's going to be x log 4 equals 2x minus 6 log 7. Now, there's something you should observe. In my first example, I wrote log 10 here. And in my second example, I didn't write anything like log 10. So this is what I want you guys to note. That when logarithm is in its natural state, you can either write log 10 or you may leave it like that, since it's in its natural state or natural form of base 10. So, unless if you have to write in any other base, like base 5, like base 7. So in this case, I must write that number. But so far it is log 10, so far it is in base 10, then there is no need for me to write 10. I may write it and I may leave it. So in case if you see questions like this in exam and you did not see any figure here, you should know at the back of your mind that you are dealing with base 10. So in this case, I will divide both sides by log 4 so that to isolate x, or to make x stand alone. So we have x equals 2x minus 6 log 7 over log 4. So I'll say this x equals 2x minus 6. So we check the calculator now for log 7. What is log 7? Log 7 is 0.8451 divided by log 4. What is log 4? 0.6021. Then say 2x minus 6. Then I divide 0.8451 divided by 0.6021. I have 1.4036. Then I'll use this to multiply what I have here. So I can say this x equals 1.4036 all into bracket 2x minus 6. What does this mean? I can multiply like this times this, and this again times this, but not to create a cause confusion, it is better if you write this figure in front so that we are going to know that this is what you are going to use to multiply everything in this bracket. So we have x equals, so I will say 1.4036 times 2, then we have 2.8072x minus 1.4036 times 6, and we have 8.4216. So we are going to take like terms. We put the value of x on our left hand side, and this figure alone remains on our right hand side. So what are we going to do? We have x here on our left hand side, and for this one to move to our left hand side, please take note that the sign will definitely change. That if this is plus, once it gets to the other side of the equation, it becomes minus 2.8072x equals, no, this one has been here before, and this is where we want all our figures to stay without the value of x. So I can say this is minus 8.4216. So from here, what do? We subtract. So let's say 1 minus 2.8072. 1 minus 2.8072. And what do I have? Okay, I'm having minus 1.8072x equals minus 8.4216. So we divide both sides by minus 1.8072 minus 1.8072. Then this goes, and from there we have so from here we have, so x will stay alone, that is x equals, so we have 8.4216 divided by 1.8072. So what do we have? X equals 4.6600. So, and that is our answer. So if you plug in the value of this on both sides, you should be able to get the value or approximately to the value. So that is that for that. Let's move on to number 3. Number 3, we have 4 raised to power v plus 2 equals 5 raised to power v minus 3. So, you know what I want you guys to do? I want you guys to pause this video and solve this. Get your figures, your answers right, then come back to this. Alright, now let's proceed. What are we going to do? The first thing we are going to do is to take log on both sides. Take log on both sides. So we have log 4 raised to power v plus 2 equals log 5 raised to power v minus 3. Then the next thing we have to do is to apply the properties. Log 4 equals v minus 3 log 5. Then we divide both sides by log 4. Divide both sides by log 4. So this cancels, and we have v plus 2 equals v minus 3 all into log 5 divided by log 4. So let's divide log 5. What is log 5? Log 5 is 0.6990 divided by log 4 is 0.6021. Then the next thing to do is for us to divide. So we have v plus 2 equals v minus 3. So let's do a quick division. 0.6990 divided by 0.6021. And what do we have? We have 1.1609. So we say v plus 2 are going to multiply. So 1.1609 into bracket v minus 3. It's the same as bringing this to the front. So we have v plus 2 equals 1.1609v minus, so let's multiply 1.1609 times 3. And we have 3.4827. So we collect like terms as usual. The letters should be on our left hand side and all figures should be on our right hand side. So we have v, this is positive. In fact, I've used one. Let's use the other one again. Let's use another method here. So now I want this v to be on our left hand side. So what are we going to do? We are going to, this is a positive figure with v. All signs stay on our left hand side. So what are we going to do to make this 1.1609v to be equal to 0? It is when I subtract on both sides. When I subtract on both sides, then I will succeed in making this one to be 0, because let's not forget that plus 2 minus 2 is 0, plus 5 minus 5 is 0, plus a number minus that same number equals 0. So if I want to make plus 1.1609v to be equal to 0, I have to subtract it because it's already positive here. So what am I going to do to make it to be balanced? I have to subtract on both sides. So I will say this is v minus 1.1609v plus 2 equals 1.1609v minus 1.1609v minus 3.4827. So this cancels and it's gone. Now it remains this figure plus 2. I don't want it to be here. I want it to be at the other side of my equation in order for me to, in fact, let me write this first. V minus 1.1609v equals, I don't want plus 2 to be here, okay, plus 2 equals minus 3.4827. Now, I have v here, I have v here. This number is not meant to be here, it's meant to be on my right hand side. What am I going to do? Since this is positive positive 2, the only way I can make this 2 to be equal to 0 is if I introduce negative 2, meaning that I have to subtract 2 on both sides. So I will say v minus 1.1609v plus 2 minus 2 equals minus 3.4827 minus 2. So this one goes, so it's gone like that, which means I can find the number here. So I will now say 1. So 1 minus 1.1609. What am I having? I'm having minus 0.1609v equals minus 5.4827. So from here, so we have then what am I going to do? In order for me to let v stand alone, I have to divide both sides by minus 0.1609 divided by minus 0.1609. So this cancels. Then I have V equals 5.4827 divided by 0.1609. And I have 34.08, and that is my answer. Let's not forget that minus cancels minus and becomes positive at the end of the day. So let's move on to the fifth question. The fifth question says 5 raised to power 2x plus 4 equals 7. 5 raised to power 2x plus 4 equals 7. So next thing we have to do is to take log on both sides. Take log on both sides. So we have log 5 raised to power 2x plus 4 equals log 7. Then we have, next thing we do is 2x plus 4 log 5 equals log 7. Then the next thing we have to do is to divide log 5. Divide both sides by log 5. So we have 2x plus 4 log 5 over log 5 equals log 7 over log 5. So it cancels, and from here we have 2x plus 4 equals log 7 over log 5. So 2x plus 4 equals, let's do a quick check. So what is log 7? 0.8451 over, what is log 5? 0.6990. So 2x plus 4 equals, so let's do a quick division. 0.8451 divided by 0.6990, and we have 1.2090. So make x stand alone. In this case, we are going to take plus 4 to the other side of the equation so that we can isolate or leave 2x. So we have 1.2090 minus 4. And we have 2x equals, so let's do a quick subtraction. 1.2090 minus 4. And we have minus 2.791. Divide both sides by 2 to make x stand alone. So x equals minus 1.3955, and that is our answer. When you plug it in, the value of x in all the questions we've done so far, you will realize that it is approximately equal to the other. So I hope you enjoyed this video, and if you like this video, please give it a thumbs up and like, share to your friends. Thank you, and see you soon.